Hello everybody, today we'll be doing the balanced binary tree. Given a binary tree, determine if its height is balanced. So we have several examples here. Let's try to see what we can understand and determine what is the difference between a binary tree that is height balanced and not height balanced. So any binary tree that left and right subtrees of every node, it differs in height no more than 1. So in this case, this 3, 9, 20, 15, 7 is going to be a height balanced binary tree. As you can see here, the difference between the left and right subtrees here is only going to be difference of 1. See the height difference between at this right subtree is going to be the height of 2, and this is going to be a height of 1. So the difference is only 1. What else? What else can we see? Let's check out another problem. In this case here, where we have starting from a 1, and as you can see, this is not too difficult to do based on what we can do with our IDE. We can still see this particular tree. So the difference is from the right side of this tree is going to be a height of 1, 2, 3, and this is going to be a height of 1. So that's a difference of height of 2, so this is going to be false. So we're looking at the height of a tree, and what happens if we have a root where there's nothing, yeah, right? So if there's a height of nothing, then we're going to return true. False and true. So everything looks kind of finicky. Let's just put some outputs and inputs here, and we can be clear about what we're doing. Output. Input, and we have the output here. Oh, it looks like the output is giving us errors. So changing up our style. So we're gonna have output up here. Input up here, and we're gonna have output on the same line. So again, input and the output. We have the input here, empty, and we have output of true. So with that, we have several cases. We have the happy case, and we have the edge cases, which is 0. With that, I think we're ready to talk about the time and space complexity that we're attempting to do this at. I think the time-space complexity that we're trying to get is going to be O of n for every node. Let's just access every node, get the height. And the space is going to be O of the height of the tree, which is log n. Because we'll be doing this recursively, trying to get the height if you have done the height before. So that's our understanding. Let's look at our match. Match is going to be recursion. The plan is going to be get the max height between 2 items, between 2 nodes, and yeah, just recursively get the height difference. If the height difference is greater than 2, greater than or equal to, if it's greater than or equal to 2, then we can just break the loop, break the call, DFS call, depth first search call, recursive call. Yeah, if we break the recursive call, then we will be able to we'll just return the height difference is greater than or equal to 2. Is less than 1. If it's less than 1, then it's true. If it's greater than 1, then well, it's false. Okay, so that's the plan. Let's implement it. I think that improves our outlook. So first, we need a value to call max height difference. I'm going to set it to 0 at this point. Sorry about that. I didn't hit the lights earlier. I think the lighting is a little bit better now. Let's just finish up this problem then. So let's create the definition, DFS call, and we're gonna take the root with an optional tree node, and we're gonna this time instead of returning a bool, we're gonna return the height of the tree. So if not root, we're gonna return 0. That's the height of the tree. And otherwise, we're gonna do a non-local. Also, we said that if it is, we're gonna have to break as well if the max height difference is greater than or equal to 2, or max height difference is greater than or equal to 2. Yeah. Because anything above that, that's going to return false for us, and we don't have to compute any more differences between heights. But if we wanted to see the max height difference between the lowest and the highest, we would want to continue, but in this case we don't. So let's take a look at the left side and the right side. So we're going to call it DFS call on the left side, and we're going to call it on the right side. What do you mean by left? I mean by root.left, please, and root.right. So with that, we have the left side and the right side. So let's take a look at the max height difference. Well, the max height difference is going to be the max between the max height difference we currently have, and it's going to be the absolute value of root of left minus right, or right minus left, doesn't matter. One thing to note is that I don't think this matters all too much, getting the max height difference, because we're going to exit anyways, so there's no point in calling this function max, I don't think, unless, you know, it doesn't work a little bit later, but we'll fix that later. Okay, so I think that's good. We have the max height difference, so what we want to do now is return the max height difference, max height between the depth between the two. So we're gonna return left or right plus 1. So with that, we are done. I think there could be a better naming scheme, and we're gonna return the max height difference, which is if it's greater than 1. If it's less than 1. If it's less than or equal to 1, then it's true. If it's greater than or equal to 1, it means greater than 1, then it's false. So that's all. I think the only thing with piece of code missing is the max height difference. We have to make that non-local because this is a variable and this is a pointer, and so we have to make this a reference item. So that's why we have to use non-local. Yeah. If we want to use a reference, we can use an array to pull in this item from this is balance and send it in. I think it was called, let me go look that up. Give me a moment. Yeah, after a little bit of thinking, it was called scope. This is this function scope, and we're supposed to bring it in. Okay, so with that, we can call the DFS call on our root, and we'll modify our height difference. Let's run our code on these example cases for a review. And as you can see, it returns all true and false for all these test cases. And so that means that this code works properly and we can submit. And with that evaluation, I think we have, oh, look, we have something wrong. Let's see what this looks like. We have a tree visualizer here to help us. And it looks like, what are we returning? We're returning true. It should be false. Why? Well, the height difference between this item and this item is 1, and this item versus this item is going to be this item here is 2, and this item on the left side is 0. So that means we should have returned false. But instead, we did not return false. I'm not sure if this will help, but this is something that we didn't, that we should have done, because this would be the case for linear type functions, but maybe because this is a binary tree that this is the case, and now it is false. Why is this? Well, I'm not sure. I'm not sure why that is the case. So maybe because the max height, just because the max height difference changes doesn't mean that we should, maybe it changes midway. By midway, I mean it changes here, it changes here, it changes here, and by the time it returns, we don't see that height difference and we ignore it. I think that is the case. That is the case. Yes. So basically, the height difference changes here, right? But because we go to the top right here, where the height difference between the two are going to be 3, right? We're not gonna find that maximum height difference here at this point, because it's going to be updated at the end, and we missed this line of code here. So if we want to just use the absolute value, we're going to say if max height difference is greater than or equal to 2, then we're going to return 0 here. And yeah, that's one way to do it. And because once we see this max height difference, we're not going to call anything anymore. Let's run it this way and see what happens. Of course, this is not a good way of running it. Let's copy. And I guess we're just playing around at this point and see if our logic is correct. And our logic is correct, but I wonder what sort of other errors that we're going to get with this type of logic. And we have more logical pain. But this is good because we're learning about what works and what doesn't. And the difference here is that we basically completely missed something again. And because we missed something and we're returning 0, the max height difference is still changing, as you can see. Because it's still changing, it causes another problem. So what we're going to do is put it here as well. Wah wah. All right. Now we have this ridiculous code that will solve this type of problem, both from the top and the bottom. Let's run it. And as you can see, this is quite extra. And it works, but this is quite extra. So what we want to do instead is to bring it back and roll it back to our original code with the max height difference. This way we don't, it looks much cleaner, we know exactly what we're doing, and the next reader for the code will have much better time reading it. So with this, we are able to get the correct answer pretty quickly. Another way of doing this is to use a dictionary to store the height information rather than to use a recursive method of storing height information for each node. Of course, that method uses O of n space because we have to store height information from each particular node. In our case, we're storing only the layer, and we're discarding it from memory immediately. So we're only using basically the log n of all memory necessary. So we're using less memory. So as an evaluation, O of n time to touch each node, and O of log n space to store the recursive call. Yep, and that's all. Because we only do one branch at a time. That's why it's log n. Okay, let me tell you why. Explain it one more time. So because when we're digging down into a tree, we only have a log n tree, right? So we just operate on these. We have a tree that operates on each DFS call, goes all the way down to the bottom, and then we basically, that's all we're going to store. After we return to this level, we don't need to store all that information anymore. We give it back to the computer. Now we're calling from the left side and the right side, right? And so now we have this layer of information, and then we lose that, and we have this layer of information, and we last with this piece of information. That's why it's log n, the height of the tree. All right, with that, I hope you learned something today. If you enjoyed this video, like and subscribe. If you want more videos, check the link in the description below. Thank you very much, and I'll see you in the next one.